let's get started. Let's see an overview of where we are. We started with this paper, Intriguing Properties of Neural Networks, and we saw that neural networks have some blind spots. But then to find those blind spots and adversarial examples, we needed to solve an optimization problem. The next paper came along and said, I'm looking for a cheaper way of generating adversarial examples. And it came up with the idea of gradient sign method or fast gradient sign method. And now that you have a fast method of creating adversarial examples, you can add those examples to your training set, or you can modify your objective function this way. That's equivalent. So the first one was an attack. The second one is trying to mitigate the attack. Then there were a couple of papers claiming that defensive distillation, or actually distillation, is a good way to defend against adversarial examples. This paper came along and said, if I change the objective function to something else, the objective function for finding adversarial examples to something else, then even defensive distillation is not going to do any good. Then we started this paper last session, and this is an extension to fast gradient sign method. For fast gradient sign method, we are apparently taking a step in the direction of gradients of your objective function with respect to input. That was the observation that this paper started with. And if that's the case, it seems like you are optimizing an objective. And then we introduce a couple of notations, our loss function, the empirical risk. And then we said, okay, now that fast gradient sign method is taking a step in the direction of a gradient of our loss function, maybe we are actually optimizing something, and maybe this should be our optimization function. Maybe we have a saddle point problem where the adversarial examples are being generated by maximizing our loss function with respect to a perturbation. And this perturbation has to be in a set of allowable perturbations. For instance, if you have L infinity norm, then these perturbations need to be small in L infinity norm, or in L2 norm, or in L1 norm, etc. And then we saw that, yes, indeed, fast gradient sign method is trying to take a step in the direction of maximizing this loss function. And our S for that particular method is defined by L infinity. It's going to define the boxes around our observations. So the idea of this paper is that you can have multiple iterations of gradient ascent. It is gradient ascent because we want to maximize our loss, but then we have to project it for us to respect this condition, because it's a constraint optimization problem. We don't want our perturbations to become too big. So rather than taking one step, we are taking multiple steps. And after each step, we are projecting it into a neighborhood of our X, of our original data point. And this was trying to give us an intuition of what is actually happening in practice. So this figure is just to give us an intuition. And the idea is that you're adding more data and you're basically augmenting your data set. And now that you have more data set, a much bigger data set, you're going to have to come up, your algorithm has to come up with a more complicated decision boundary for it to respect and be robust to perturbations of your data points. So now if you take this data point and perturb it a little bit, that decision boundary is going to respect it. If you take a data point here, for instance, this is star, this red decision boundary is going to respect and it's going to classify that correctly. But that other classifier is going to fail. And this is going to be an adversarial example to this classifier. So let's see some results. These results are a little bit different to what we are used to. Now you have a network that is trained using projected gradient ascent. So it is adversarially trained. And basically we are using this objective function. Now the question is, what type of an attack is more effective against a network trained this way? So our network is already trying to be robust because we are solving this objective function rather than the empirical risk. So our network is already including these boxes around the data, and now we want to attack it using different methods. You take natural images and ask the adversarially trained network to classify it. It's going to give you 98.8% accuracy. So there is no surprise because if you take a natural image, it's already one of these images in the box. It's actually this blue dot, and we're comparing it against this decision boundary, the more complicated one, and it's giving us 98.8% accuracy. So these are real images, natural images. Now you can take your images and attack them using fast gradient sign method. So for each image, you're going to have an adversarial example. You take that example and ask the robustly trained network to classify it. And yes, the accuracy is going to drop, but it's not that bad. If you do projected gradient ascent to attack this network, it's going to be 93.2% accurate. So this network is robust. That's the idea. The accuracy is still high. If you do more rounds of iteration, basically take more steps of your projected gradient ascent to come up with an example, the accuracy is going to drop a little bit, but still the network is robust. And you can do PGD with multiple restarts. So each time you're going to have a random restart to your initial perturbation. And as you can see, these are becoming more costly. Natural images, there is no cost to it. To come up with adversarial example, you're just feeding your natural images. Fast gradient sign method is really cheap. This one is more expensive because you have to take 40 steps. This one is even more expensive, and this one has restarts for it to become a more effective attack against this network. And what does this A mean? A means you're doing a white box attack. It means that you have access to your network, to the parameters of the network, to the hyperparameters, to the structure of the network. So these are white box attacks. You can have a targeted attack, and the most effective attack in this result seems to be PGD with 100 steps and 20 restarts when you have access to the network itself. And CW is the attack from the previous paper. Let's see. Yeah, it's called CW because of the name of the authors. It's Carlini and Wagner. So it's CW, it's this paper. Now let's go to the next part of these results and try to interpret them. A prime means you have a black box attack. What does it mean? You have an independently trained copy of the network, and you train it independently. You have a copy of the network, you train it independently. And what does B mean? B is a different architecture. It's a totally different architecture. You use a totally different architecture to come up with attacks, to come up with perturbations of the images. So for A prime, everything that you see here is a black box attack, and the most effective one is still PGD. And we know that our network is being trained using projected gradient ascent.
Can I ask a quick clarifying question?
Sure.
So in this second set of results here, are the adversarial attacks being developed on the original network, or are they being developed on this independently trained network?
So they are being generated using the independently trained network. It's a copy of the original network. You don't have access to the original network, but you know that the network is, I don't know, a Google net that is that has this many layers and is that much wide, etc. So you know the details. You make a copy and you train it yourself.
But if you're training the adversarial, like if you're coming up with the adversarial examples on the independently trained network and then attacking the independently trained network with those adversarial examples, shouldn't you be getting the same accuracy as with the other set of examples where we trained it?
No, you come up with adversarial examples using the copy of the network, but then you're attacking the target network.
Oh, okay, the original one. Okay.
Yes.
Okay, that makes sense. Thanks.
And so when you say it's a copy, does that mean they're the exact same structure but just trained sort of independently?
Yes, exactly.
Okay.
The exact same structure, trained independently. And I believe the data set is the same data set also.
So that's just showing that the slight sort of non-deterministic sort of structure of training doesn't affect it as much.
Yes. So in the best case scenario, if you are an adversary, you want to have access to the network itself, because then you're going to come up with the most effective attacks. That's going to be a white box attack. For a black box attack, you don't have access to the network, but you know what network that particular company is using in their production. you create your adversarial examples using this network and use that to attack your original network. Does that make sense?
Yeah.
And B is the case that, yes, it's a black box attack. You actually don't have any information about the architecture that they are using.
Wouldn't you expect that with using B, the sort of degradation and accuracy should be much lower, but it's actually better than A prime? Like, how are they able to use a totally different architecture, but then get a better success rate in being adversarial?
See, this FGSM here is having 95.6 accuracy, and this FGSM attack is having 96. The PGD, let's compare apple to apples for A prime. This one is more successful. It's not being more successful, it's actually, you need to look at the error rate. So these are actually less successful at attacking this network. Let's look at this PGD, and there is another one here, I guess. You can compare this to that. This is 89.3. This is 95.7. So it's actually, these numbers are higher. It means that the attacks are, a black box attack is less effective, because then you need to look at the error rate. So a white box attack was more effective at lowering the accuracy, and a black box attack is less effective. So I think it should be more clear now. Yes? So I don't see any contradictions. So does this make sense? Same thing is for CW. There is CW here, CW here. You can compare apple to apples. This is 97. This is 94. So a white box attack is more effective. If you have access to the original network, you are going to come up with better adversarial examples, more effective. And it's going to drop the accuracy more compared to when you don't have access to it. So to be fully transparent, this is your original network with A prime. We don't have access to A. We generate examples using A prime, and we are attacking A. So you generate examples using B, and you attack A. So are we all on the same page? Yes, this table is a slightly different compared to what we are used to, because we usually attack networks and we want, and the network is never trained to be robust. Now these networks are trained to be robust, and we are still attacking them. Okay. And same thing for here. This number is lower than this number. I guess let's look at PGD 41B, PGD 41A prime. So this one makes sense. So we are being less effective. CW plus, I think they don't have any steps. Probably you cannot compare these two together. FGSM is a little bit out of the pattern, but it's just an example. This could be just an outlier, the way the networks are being trained. But it turns out that among these methods, FGSM is the most effective one at attacking our network that is trained to be robust. When you don't have access to the network and it's a black box attack, and you're using a totally different architecture.
How do you get gradients when you don't have access to A?
So
you just use the gradients of B?
Yes, you use the gradients of B.
Yeah, I feel like it seems like that would work less well, but for some reason it works better. I'm still a little not fully understanding why that is.
This one is an outlier, so I wouldn't count too much on this.
Okay.
The rest of it, the pattern is clear.
Well, it could be that the A and the A prime architecture are designed with this diagram on the left, where you're including a region in a box around every single example, and so you're training the network to recognize images and also their neighborhoods. And if B was a network which didn't train that way, where you were just finding a boundary right in between examples and not necessarily including their neighborhoods, then any kind of attack could be more effective, because they're not built to be robust to attacks.
But I thought we were still attacking A, which was trained sort of with the curved line, but just using examples from B.
Yes. So we're still attacking A. So let's have an example in mind. That's going to clarify things. And the example is for a self-driving car. There is a company that has created a self-driving car, or the system behind it, and the vision system behind that self-driving car. And let's say they are using ResNet 100 for their vision. And that network is trained to be robust, because the company wants to avoid adversarial attacks. So that network is fixed. Now, let's say we are the adversary and we want to attack that network. We want to change the images that the car sees on the fly. So we want to add noise to the images that the car sees and, I don't know, maybe make a mistake when it comes to stop signs. And then it's going to lead to accidents. Now, what are we going to do as adversaries? There is a network that is fixed, that is mounted on the machine, on the car. Now we want to attack it. Let's say we are a very effective adversary and we have access to the architecture of the network and we have access to the data that the company used to come up with that architecture. That's going to be a white box attack. And that's, by construction, is going to be the most effective one because you have access to every single detail. Now you come up with adversarial examples using these methods and you're attacking the system on the car and you're able to lower the accuracy. It means that that car is sometimes making mistakes in recognizing stop signs. It's not 100% effective, but you manage to hurt the system. Now let's say you don't have access to the architecture. You have access to the architecture of the network that is mounted on the system, but you are going to train your network independently from scratch. And there are going to be some random effects going on because maybe your data sets are different. Maybe the way you are training it is different. This is going to be a black box attack. But remember, we are still attacking a network that is trying to be robust and is already in production. So this is going to be black box attacks. Black box attacks, because you don't have as much information as white box attacks, are going to be less effective. And the thing is that you cannot compare this 96 to that 98. I guess there was a mistake here. We should compare FGSM to FGSM. And now you see that this is less effective. You should compare PGD to PGD. We should compare apples to apples. So it's the same attack, but you came up with these attacks using your own version of the network. But then things could be even worse. Your life as an adversary could be even more complicated. Maybe you don't even have access to the architecture that they are using. Maybe they are using Inception. Maybe they are using ResNet 100. You can, on your own computer, come up with Inception. You train Inception on your own data. You generate some images or the perturbations to the images, and then you attack the original network. Does that make sense now? I want to hear.
Yeah, I think
yes, go
it makes sense. If you ignore that FGSM line, I think it makes sense. But that one is still confusing me.
But this could also be reasonable. You're right, because you don't have enough information. This one should be lower or should be higher. The thing is that we don't know. Maybe our Inception network is a more powerful network that those guys are using in production. I wouldn't read too much into this. This could be an outlier, or this could just be a phenomenon because of the type of the network that they're using. And we should remember that these adversarial examples are general. We saw that in the first paper, and that's why there are serious problems. Regardless of the architecture and regardless of your training data, they are universal. So they are generic examples. I think we spent a good amount of time understanding this table, and now it should make sense. Everything should be clear. This is a similar table to the previous one. For the previous one, we were using epsilon, this epsilon here, to be 0.03. Here we are using a bigger epsilon. And as you can see, these numbers drop from 98 to 87. So now we are making the space of perturbations a little bit bigger. And now these attacks are becoming even more successful. And by the way, the network, the robust network, is trained using epsilon being 0.3. And we were attacking it with the same magnitude of an attack in this table. Here we are increasing the magnitude of the attack. These are bigger perturbations. So does this make sense? And a NAT here is a copy of the original network trained on natural examples. So if you train on natural examples, they are going to be less effective. And let's see how important is this epsilon when it comes to attacks. I'm going to take a look at the blue curves, and this is epsilon. The network that is mounted on the car is trained using projected gradient ascent with epsilon of 0.3. So that's this horizontal line. So attacks with epsilon less than that number are less effective compared to when you increase the magnitude of your attack. So it's the story of this table compared to this table. And you see so that one was for L infinity norm. You can change to L2 norm. These are for n list. You are going to have a similar pattern. Now your epsilon is, I don't know, around 8, and you're having a network that is trained on CFAR 10. This is L infinity norm, L2 norm. And the blue curve is the one that I'm interested in. Any other questions or any questions about this paper before I move
So
to
just to make sure, as epsilon gets super high, the image becomes just pretty much noise at some point, right? So it makes sense why it would drop to almost 0.
Yeah, so if given enough noise, any system can break. But these are smart noise. Each image is going to have its corresponding noise.
Right.
Any other questions?